Hello ladies and gentlemen, welcome back to Lab 9 for GGS 300. So today what we're going to be doing is we're going to be doing a little bit of work within ArcMap. So what I've done here is I've downloaded the data from the Blackboard website for GGS 300, so you should have this Lab 9 data here and you have these directions as well. So within the PDF, this is basically just giving us a bit of an overview as to what we're going to be doing today. So we've got two different data sets, and first of all what we're going to be doing is doing some nearest neighbor distance analysis for Austin, Texas, and then secondly we're going to be focusing on a kind of US-wide assessment of some demographic trends, okay? Focusing mainly on looking at autocorrelation issues, okay? So that's the actual data. I'm going to start ArcMap up, and I've got a version of it here, ArcGIS Pro, which you should have a version available to you, or you should be able to just log on to the GGS remote laboratory and access a version there. As you know, I'm an open source fan, so generally I'm using QGIS for a lot of my own work. Quantum GIS, so it's an open source alternative to ArcMap, and it's very good. I would recommend you take a look at it once you've finally got the hang of doing this, doing a lot of the processing within this. But anyway, that's something to focus on in the future. So let's just take the first data set, nests, and I'm just going to drag and drop it into my ArcMap window here. So let me just get this right. There we go. So these are all of our nest points. Let's just think geographically where we are. Okay, so we've got the great state of Texas here. We're zooming into Austin, Texas. Very nice part of the world to be in. I love Austin. And here we have a set of data, and those data are basically nesting sites. So you can take a look at the points that we have here. So there's information for the type of cover, the bird age, etc., the number of eggs each nest site had, so on and so forth, hatch year, weight, etc. So what we're going to do is we're going to run some measurement analysis on this data. So we've prepped the data here. We downloaded the data from Blackboard. I'd already unzipped it for you, so don't need to worry about that. We dropped it into ArcMap, fairly straightforward. That shouldn't be too complicated for you now. We opened up, and we're going to start doing our nearest neighbor analysis now. So we've got the bird's nest. It's actually in Travis County, Texas. Okay, I said Austin, right? It's right on the border, northeastern border of Austin. The question is, though, are the nests randomly placed in a neighborhood or not? Okay, so we're going to state the hypotheses for the tests which we're going to run. You'll remember that we went over these within the lab session, so sorry, within the previous lecture session. So it should be fairly straightforward. We want to get this Zn test statistic, and we need to do that by basically getting the observed mean of the nearest neighbor distance and the random mean of the nearest neighbor distance, and then the standard error, okay? And we're not going to do anything too complicated today other than state the hypotheses, okay? So that means that if it's the null hypothesis, we expect that the nearest neighbor distance is basically equal to what we would randomly expect, so there's no difference there. The normal kind of status quo approach. Whereas the alternative hypothesis is that we would expect something quite significantly different from that kind of random distribution of points and the kind of the mean nearest neighbor distance that we would expect to obtain from that. Okay, so then what we need to do is we need to kind of chip into some of the nifty little tools that we've got within ArcMap. So we need to go to the spatial statistics toolbox and then go into look at actually analyzing patterns. So we need to go to analysis, tools up here. We then need to go into toolboxes, spatial statistics, analyzing patterns, and then once we're in here we need to look at the average nearest neighbor. Okay, so that's the particular tool that we're going to go in and grab. So nests is the input feature class, so we need to state that. So nests, there we go. And we're going to basically generate a report, and we're going to enter a 600,000, it's actually feet, square feet for the area. So you can tell that when I close, sorry, one second, let me just close this. There we go. So you can see we've got the coordinate reference system here for eastings, northings, it's feet US for the XY coordinates. So we can put 600,000 square feet in as the area nests. We're going to run it. Review the details. So what do we get as our output? So we've got the results. First, we're going to look at the observed value. Okay, so the observed mean distance, it's 9.46 here, which corresponds to what we've got in here. We then want to look at the expected value, which is 21.9, which nicely corresponds with this. We can then get the NN, the nearest neighbour ratio, so the R ratio, so that's 0.43. The z-score, which in this case, as it's stated here, is minus 19.2, so it's really quite strong. And then we have a p-value of 0. Okay, so really quite significant. So that's quite a very, very strong result which we've obtained there. So we've looked at the report. Obviously, as we've got really quite a significant p-value here, we're going to accept the alternative hypothesis. We're going to reject the null hypothesis and accept the alternative hypothesis at the 95% confidence interval. That the placement of these nests is not random. Okay, so I just have this catch down here that they appear clustered. Well, obviously that's what it looks like when we look purely at the nesting sites, as we've done here. But the key point is that we didn't actually test for that. We just did a two-tailed test. We didn't say whether clustered or they're dispersed. We just said that they're significantly different from the random distribution that may occur at random. Okay, so we can rerun this without any information for the area, as we're doing here, and we're able to compare this. So we basically just use the smallest bounding box. So in this case, we still have a highly significant result. There's a very, very small change to the z-score. Okay, so it's larger this time. It's more negative. It's increased in its magnitude, but in the negative direction. We have a slightly different ratio change, but nothing particularly major coming from that one particular change. Okay, so now what you're able to do is, if you want to, you can save this ArcMap document, but as we've got a different projection system here, the quickest way for us to exit it in order to work on our new data set that we want to analyze is just to exit straight out of ArcMap. So you can choose to do that however you want, but now we want to start working on the Moran's eye. Okay, so we just need to open up a fresh test. What we want to do is want to get the low 48 county .shape file. So if I go to our lab data here, we have this, see it says SHP shapefile there. You see it's the largest one as well, it's like 75 megabytes. So if we just drag that and drop it in here, and actually you see the file I dropped in is below the is below the topographic layer. So just if I just reorder them like that, then the low county layer pops on top of the topographic map that we've got. Obviously the map just provides us with a little bit of context here. And we've got all of those counties for the contiguous United States. So let's run the Moran's eye now. So we've imported our data. Let's go into symbology. So we need to go over here, right click. My bad. Symbology. Here we go. And once we get in there, we want to go to quantities and graduated color. Graduated colors. Okay. And once we go in here, we want to pick the field for Hispanic. So here we go. So you can look at any of these demographic trends if you want. Now, in this particular example, we're just going to normalize against the population for 2000. So we're able to normalize there. So this is the percentage of people who register as Hispanic relative to the population 2000, okay? So now we're able to look, compare it to a different data set. So here, obviously, what we're doing is we're looking at the proportion of Hispanic people, and it's going to be highly, a priori, it's going to be highly geographically correlated based on flows of immigration. Okay, so we know what that pattern's going to look like before we start to analyze the data, but here we're actually able to look at that spatial pattern, and obviously it's quite significant, and there's quite a significant difference between, for example, those border regions of California, New Mexico, Arizona, Texas, and also southern Florida, relative to maybe some of those other states that are either in the South, for example. If you look down Mississippi, Louisiana, Arkansas, Tennessee, Georgia, Alabama, these states don't have very high immigration, very high levels of immigration, at least for Hispanic people, based on the measures that we have here, so normalized against the year 2000 measures. Okay, so quite strong spatial autocorrelation, just kind of a priori eyeballing the data. Okay, but we're able to actually test this. So before we do that, let's look at something different. So that's the Hispanic rate across all of those really quite granular US counties. But we're actually also able to look, for example, at the male rate. So let's try for males relative to the population for 2000. We're actually able to do that using a rate as well. So we've got the male rate down here, showing the rate at which we've got males. I mean, it doesn't seem that I couldn't really work out the trend on this. I mean, I wouldn't expect there to be a massive trend, and these are really small numbers anyway, so I'm not looking into it too much. But obviously, you have this quite large correlation in this kind of Middle Western area here, and I can't think of too much logic as to why that would be. Okay, so we're able to compare these different metrics. So we used the Hispanic rate, so we used a pure Hispanic metric, and then we compared it to the normalized version for the year 2000. And then we're also able to do that for the male rate, for which I'd created an existing metric. Okay. Once we've got these, what we're able to do, and we've kind of explored them spatially, so we've done that with the other tests that we've done. I've always emphasized that we need to look at the data and eyeball how we kind of feel about the data before we run the tests, which is why we do things like scatter plots or box plots, in order for us to get some kind of understanding for what the data is trying to tell us in advance of actually running the kind of more formalized tests. Okay, great. So now we can go to the actual spatial statistics toolbox. So if we go in there and look at analyzing patterns, we're able to actually run Moran's eye. Okay, so let me bring back up the Hispanic rate for us to start. There we go. And sorry, the spatial statistics toolbox. Let me go back to analysis. Toolbox up here. Toolboxes. Spatial statistics toolboxes. Analyzing patterns, spatial autocorrelation. Great, so for our input class, we can place in the low 48 county layer that we have. This time round, we're actually going to look at the Hispanic rate, so we need to pick that out just here and generate a report. But we want to only use the contiguous edges, contiguity edges only. Generate report, and let's run this for Moran's eye. So it's taking a little bit of time, but this will almost certainly show up in the next couple of minutes. So my wife actually, she has a history background, so she absolutely loves studying the kind of food trends that come with migratory rates. Okay, so one of the great things about people coming from other places is that they bring with them their own cuisine, their own food. So, if you look at the food flows across Europe, for example, there's that one kind of very classic British dish, which is fish and chips, so fried fish and fried chips. And actually, the reason why that's ended up in the UK, it was brought over by Eastern European Jewish migrants about 200 years ago, and it was actually adopted here and became our national dish at one point. And I think also you've seen very similar trends actually with the kind of the wave of Turkish migrants across the continent of Europe, and how people eat. Many more restaurants serving kebabs as you call them in the US. So essentially, you have those waves of migration, and that very much changes the food cuisine of those different places. So what's really indicative of this map here is that, there's incredible food diversity along the border region for anyone who's actually been down there to travel that area, which I have, at least for different portions of it. I've not traveled the full border, but at least the Californian and Texas portions, I've been down there. Okay, so what we did was we ran this global Moran's eye test using just the contiguity edges, and here what we get is a z-score of 74.8. Okay, so we also get that's incredibly high, and we get this p-value obviously of 0 as a consequence. And what this is also suggesting, because we have this index of 0.82, is that there's a really quite significant positive spatial autocorrelation for this one particular metric. So now we can run the same. So let me just go back to the case here. So what we ran was the Hispanic rate contiguity, and now we're going to run the same but with the inverse distance. Okay, sorry, before I get ahead of myself. So now we're going down here and we want the inverse distance. And what we want to do is set the inverse distance band to 200,000. Yeah, so this. So we're in meters here. So 200,000 is 200. Yeah, so that should be right now. So that's 200 kilometers. Yeah, because we're in meters. So I just checked again down here at the bottom of the screen. So you see we have the easting and the northing coordinates, and we have the little m down here, which is quite handy. It's indicative of the fact that we're using a projected coordinate reference system. Okay, and when we open this up again using this inverse distance weighting, we get an incredibly high z-score. Again, the index has slightly changed this time round, but still a highly significant p-value. So, this metric is telling us that we have very strong autocorrelation here, okay? So, we can now also try with the male rate. So let's just swap this here for the male rate. We're going to use the same weighting factor, and we're just going to run it exactly as it is here. We're going to see what results we obtain. So we run it again, and this obviously tells you exactly what we've run. So the input field was male, generate a report. We used inverse distance weighting. We used the Euclidean distance to measure the actual straight line distance, and we used a distance band of 200 kilometers. Okay, and we get this index of 0.11, so it's quite a bit smaller, but still a very high z-score, and we still get a significant p-value for this particular case, so that's quite interesting. So now we're able to progress onto actually mapping these clusters. So in both of these cases, what we've looked at is how much spatial autocorrelation is present. Obviously, we've had significant findings for all of those tests that we've run, in which case we would reject the null hypothesis and we would accept the alternative hypothesis that there's quite, these results haven't just occurred by random, okay, in essence. Okay, so let's move on now, and let's just actually do some nice mapping just to close this this lecture off. So there we were doing the kind of formalized statistical tests in order to understand the level of spatial autocorrelation. So this is something that you should do prior to, for example, running a set of regressions if you've got spatial data, just to check whether you might encounter some sorts of spatial autocorrelation issues. But also what's nice is to be able to show where those actual outliers may exist. So we're going to go back into the Spatial Statistics toolbox. We're going to look at the mapping clusters set of options. Here we go, and we're going to look for the cluster and outlier analysis. So here we go. So now we've opened that, we're going to place in our low 48 county data field. We're going to find the Hispanic rate, which we've got here. So if we go down here, then we end up with the right metric. We then want to use inverse distance weighting, which we're doing here, and we want to apply this distance-based threshold, which is going to be 200 kilometers again. Okay. So this time around we should be able to run, and fingers crossed, run smoothly and relatively quickly. Here we go, fantastic. Okay, so what this is basically telling us, if we go back to the results that we had in the lecture. So remember, we did this fairly standard statistical test in order to look at community segregation in Michigan, which came out very strongly, but just kind of gave us this this kind of single set of global Moran's eye statistics. Fine, this is kind of what we've done in this new set using these two different rates. So one is the Hispanic rate and one is the male rate. Then what we're also able to do is to run the kind of local Moran's eye assessment in order for us to categorize those places that sit somewhere within the distribution of the Moran's eye scatter plot. Okay, so this gives us some indication of those areas which are highly positively correlated, or they actually have below average positive correlation. So essentially what we're seeing here for these high clusters are areas which are above average clustering, and the areas which are low in terms of clustering. And then we have a set of outliers. So these are areas within those either high or low areas which particularly stand out. So maybe they actually have low Hispanic rate, but they're in a high autocorrelated area here, like this, or vice versa. If you're in a low in a low autocorrelation area here, but you have quite a high rate, then maybe you're highlighted basically in this red shaded box here. So I kind of like this because it gives you that kind of nice graphical understanding of what's happening underneath the hood, okay? And it's showing those areas that actually have statistically significant findings. It's just kind of graying out, or whiting out in this case, not providing a color for those areas that we just don't have significant findings for. And you know, at one end of the stick in geography, you have areas where you just color shades based on some underlying metric. Fine, that's kind of basic, what you do, you know, when you're just starting out. And then the other end, you have some really hardcore quantitative spatial science techniques. And I kind of like this because it's a very simple quantitative method. So it's kind of moving along that trajectory towards more complex, but then you're able to actually here kind of graphically show where those local areas sit within that distribution that you're analyzing based on the level of spatial autocorrelation. And I think that that's kind of really positive because it's you know, it's good for you to understand, and it's good for you when you're working on a particular application, as well as just understanding the method as we are here. Hopefully that's fairly clear for you. So I'm going to wrap this up now. We've been through basically everything that was within the relatively simple laboratory walkthrough sheet that I put together, which you can download and you can walk through yourself. There will be an assignment on this work, so you'll need to have a go at that and submit it before, I think next week, I think it's the 22nd of April. Don't hesitate to reach out to me if you've got any further questions. I'd love to hear from you, and I look forward to seeing you soon, and good luck with the work, and hopefully it'll only be a few more weeks until semester's over, and then next term we can all be back in the classroom together. So have a nice day, and I'll see you all soon. Goodbye. Thank you.